Okay, so here we are, continuing our discussion, kind of using what we talked about in the last PowerPoint as a bit of a springboard, right? So we're going to riff off our discussion of scatter plots and correlation. We're going to take that work and we're going to extend it. We're going to extend it in this kind of really cool, very useful context referred to as simple linear regression, or sometimes said a little more technical, a little more hoity-toity, the least squares regression line.
So recall from our earlier slides that if the absolute value of that correlation, the absolute value of R, is really close to 1, which basically means that the correlation is either close to 1 or minus 1, then that implies there's a strong linear relationship between X and between Y. So for example, let's kind of take a look at another example. Let's say that the temperature in Fahrenheit and weekly fuel consumption of natural gas measured in tons is recorded for 8 weeks in Philadelphia with the following results. So there we are. The first week it was 28 degrees on average that week, and the overall fuel consumption was 12.4 tons. Second week, same temperature, but for whatever reason, people used a little less gas. Then it was a bit warmer. Since it was warmer, well, people still used about the same amount of gas, and so on. Now remember, when you're looking at this type of data, you should really always start with a plot. A plot gives you an idea, right, the scatter plot of what's going on. And so here's a scatter plot, and what do we see? Well, let's think back. What is a scatter plot supposed to show us? It's supposed to show us form. Is there any type of form here? Well, sure, yeah, it looks like there's a sort of straight line relationship. What's the direction of this straight line relationship? Well, it seems to be going in the negative direction, right? That is, it seems to be approximating a line that would have a negative slope. Basically, that means as, oh, whoops, alright, bad professor, I forgot to change the labels. This is using the observations from the last slide, but I still had it labeled height and weight. That x-coordinate should be temperature, that y-coordinate should go ahead and be fuel consumption. So what we see is as our temperature increases, we see that the fuel consumption decreases, right? As it's getting warmer and warmer and warmer, people are using their heater less and less and less. How strong is this relationship? Well, right, this is where the correlation is actually very useful, but I would say this is actually very strong. All those points seem to be really pretty tightly packed in this sort of linear form. What's a good guess for a correlation? Well, I know it has to be negative, since it's a negative relationship. It's pretty strong, so I would guess maybe somewhere about negative 0.9. If we put the observations from that second slide or so into a calculator, into some software program, it would tell us the correlation is negative 0.94841. So let's just go ahead and call that negative 0.95. That is very strong, a very strong negative relationship. Now remember, the scatter plot, this is how we're going to tie this back into the last chapter. The scatter plot approximates a straight line relationship. A natural question then becomes, well, what is this linear relationship that it fits? That is, right, what is like the line, the single best line that fits this particular scatter plot, right, as perfectly as possible? How do we find the line that best fits a given scatter plot? Well, what's typically used in practice is this thing called the least squares criterion. So the best line satisfies this least squares criterion. The criterion basically says that if you look at the sum of the squares of the vertical distance from all data points to a particular line, the best line makes this value as small as possible. That's the idea. Least squares. You square the distance, you add them all up, and you look for the line that has the smallest, the least value. If you want to see a picture of this, you could look at 488 or 488. The basic idea is you draw a line, and you measure vertically the distance from every point to that line. If the line fits the data really well, it's going to be really close to all these points. That vertical distance should be pretty small. Now, why don't we just add the distances? Well, it's because some points are above the line, means that they have a positive distance. Some points are below the line, which means that they have a negative distance. So if we add them up, all these positives and negatives cancel. To prevent that cancellation, we square it. Very, very similar to kind of why we squared distances when we calculated the standard deviation. Now the equation of the least squares regression line is this. Y hat, remember that little symbol's the hat, equals, remember that's the Greek symbol beta in the 0, so we would call that beta naught hat. I know, kind of crazy. Plus beta 1 hat times x. Now, this is just different labeling of what we already know from math class. Remember, generally in math class you call it y equals mx plus b. So, the number next to the x, that's our beta 1 hat, that's the slope of the line. The number by itself, that's the beta naught hat, that's the y-intercept of the line. So, I mean, even though it has different labels that are a little bit unique to statistics, this is nothing more than what you've probably done hundreds of times in your algebra class. The y-hat, we just put a little hat on it to emphasize that it's a predicted value of y for a given value of x. We'll get into more detail what we mean by that in a little bit. So, one of the primary uses of this least squares regression line is finding this intercept and slope and using their interpretation. So how do we interpret these things? Well, the slope always has the same sign as the correlation. Makes sense, hopefully. Right? Since we said the correlation measures the direction of the relationship or the direction of the association, in the direction of the association we said, well, that's essentially just the slope of the line. We can interpret the slope as the rate of change of the response variable as the explanatory variable changes. It basically tells us how many units do we expect y to change for each 1 unit change in x. The intercept, this tells us what we expect the response variable y to be when the explanatory variable x is 0. Sometimes this is sensible, sometimes it's not. Think about our height and weight example. Is it sensible there? Probably not. The intercept in that case would be interpreted as, what do you expect the weight to be for someone who's 0 inches tall? Well, it's kind of a senseless statement because I don't think there's anybody who's 0 inches tall. I think even our imaginary friends, when we imagine them, they have some sort of height to them. So, right, in that example, it doesn't really have a nice interpretation. It's still mathematically useful. One of its uses is it helps us draw a regression line. Remember, from math class, if we know any 2 points on a line, we can always get the whole line just by connecting those points. And 2 points that we know are always on a regression line are that y-intercept, 0, and that beta naught hat. Here I called it A, something a little bit easier. And the point x bar, y bar, the sample mean of x and the sample mean of y. Both those points are always on your scatter plot. So you could always plot those, and then you can get the line just by connecting those.
Okay, so for our particular example, what is the slope and what is the intercept? Now, in practice, right? In practice, there are formulas in our textbook. You could take a look at them if you're a formula type of person. In practice, people are not computing these formulas by hand. In practice, they're really not even using, at least a basic calculator where they're adding and subtracting and multiplying numbers. Maybe they're actually putting the observations in a more fancy TI-83, TI-84 calculator, which will then do all the calculations behind the scenes for them. Probably even more likely, they're using some sort of statistical software. Excel, Minitab, SPSS, there's lots of different statistical software packages out there. So in practice, right, we would take the information, the observations we had on the previous slide, we'd put it in Excel or SPSS, for example, and we would let that tell us that for this particular data, the slope for our least squares regression line is going to be negative 0.1281. Now, first off, is the negative sign surprising? No, of course it isn't, right? We observed way back when that the correlation was negative. The slope and the correlation, again, always have the same sign. Since the correlation was negative, the slope had to be negative. And we also find that the intercept for this example is 15.77, and we'll interpret each of these in just a few slides.
So the equation of our least squares regression line would look something like this. Y hat equals 15.77 minus 0.1281 times x. How do we interpret these? Well, we can start off by interpreting the slope. The slope is very powerful in terms of its interpretation. Right? Correlation by itself just tells us as one increases, we expect the other to decrease. Slope is more informative. Slope says as one increases, how much do we expect the other to decrease? And it turns out that here we say, well, when temperature increases by 1 degree, we expect gas consumption to decrease by 0.1281 tons. Remember, it's a decrease because that slope was negative. The intercept says, well, if the temperature were 0 degrees, we would expect the gas consumption to be 15.77 tons. This actually maybe is more meaningful because it can be 0 degrees outside. So one use of the least squares regression line is figuring out the slope, figuring out the intercept, and being able to interpret these in the context of our problem gives us a better idea, right, of how to quantify the relationship between these. However, there's more. We can also use the least squares regression line to make predictions. And there's two types of predictions. One is interpolation. So this is predicting y values for x values that are between your observed x values. Extrapolation is predicting y values for x values that are beyond your observed x values. So let's go to our original example. How much gas will be needed if the weekly average temperature is 45 degrees? It's really powerful to be able to answer this type of question, isn't it? Imagine you're Pico, and Pico gets their gas from someone else. They have to sort of try to figure out, to the best of their ability, how much gas they should have on storage every week to sort of fulfill the need of everyone. They don't want too little because, of course, they don't want to run out of gas, but they also don't want too much because there's storage costs and other things like that. So Pico would like to sort of try to be able to predict what's the gas consumption going to be next week. How do they do that? They look into a crystal ball? Of course not. What they do instead is they exploit the extremely strong relationship between temperature and gas consumption. They go on weather.com. They look at the weather predictions for next week. Maybe it predicts next week is going to be 45 degrees on average. And they say, okay, we can use this information to get a pretty good prediction for how much gas we're going to need to supply Philadelphia, and that tells us how much to have on hand. The follow-up question we want to ask is this interpolation or extrapolation? So here I was a little lazy. Y hat, I just wrote out the word hat, is equal to 15.77 minus 0.1281. To do the predictions, it's as easy as just plugging the number in for x. You plug in 45, you put that in your calculator, you get 10.0055. The x values from the original data set range from 28 to 62.5. You can go back and take a look at it. It's like that first or second slide. 45 is within these bounds. That means that it's interpolation. How much gas would be needed if the temperature was predicted to be 20 degrees? Just plug in the number 20. Throw it in your calculator. 13.208. That's a higher fuel consumption than before. Is that surprising? No, of course not. the temperature has gone down from 45 to 20. When we did that, right, we would expect, because it's a negative relationship, fuel consumption to go up. Now note that the range of values in our original data set, the smallest x value was 28, you can go confirm that. The largest was 62.5, you can confirm that. Notice 20 is outside of these bounds. Hence, this is extrapolation. Hopefully we see the difference there. Now the extrapolation is probably not too bad here because 20 is not too far from 28. But the farther you get from these bounds, kind of the worse your prediction is going to be. In general, extrapolation is more risky than interpolation. We can maybe imagine why that is. That is, we see a negative relationship between gas consumption and temperature, but our data only went to 62.5. We might imagine when you start hitting the summer months and it starts getting hotter, 80 degrees, 90 degrees, 100 degrees. Well, now people aren't running their heater, but instead they're running their air conditioner. And I think Pico also supplies gas for air conditioners in a lot of places. So what we might see is that once you hit the summer months, you kind of have a different relationship. That is, the fuel consumption is no longer decreasing as it gets warmer, but the fuel consumption is actually increasing. That is, if we were to draw a scatter plot maybe from temperature ranges that went from 28 to 100, we might see what? We might see, I guess it would be a happy face pattern, wouldn't it? Yeah, it would. Starts out decreasing and then ends up increasing. So using this equation to make a prediction for the fuel consumption if it's going to be 95 degrees is probably a bad idea.